Okay, so here's our first problem, and it's kind of a doozy actually. Their little first problem they throw. It's not really a doozy, but some things I wanted to point out. Notice how they put the charges in absolute values. Okay, they're putting the charges in absolute values. So notice we've got a proton here. We've got a hydrogen atom here, and we've got the electron orbiting about, and this will be the problem we'll stop on. Okay, this will be the problem we'll quit on today. So we got this electron out here. We got this, and we're going to take it right at this moment, right here. We're going to calculate what that velocity is. You might be going, wait a minute, what the heck is this? I'll show you. But notice, positive charge, negative charge. So what are they doing? Are they attracting each other or repelling? They're attracting each other. In other words, that electron wants to collide, wants to smash its way down in there to the proton. But why is it not doing that? Because of its angular momentum around the outside and the quantum mechanics that's going on. However, the theory, but if we look at classical theory, eventually it's going to spin its way right into the center, but that doesn't happen. In fact, it might even change its orbit, it might even jump out here. So that's what we wrestle with in modern physics. But right now, we're just looking at negative E times positive E. So I'm going to just, and 5.29 times 10 to the negative 11. So I'm just going to do this problem and show you and why we do it in absolute value, okay? Because in physics 250, in the engineering physics, they mess with matrices and all that and plug the things in and multiply it out, and they get the correct direction of the sign. We don't need to do all that. And we're going to do the exact same damn problems they are. But what we do is, because we're smarter than they are, not being ornery, but we're not smarter, but we don't need all that extra mathematics when we can draw a frickin' picture and figure out which way the forces are going, all right, and decide. So that's why we put everything in absolute value, because we'll always do a positive number, and then we'll look at our picture and decide which direction it's going, okay? So here we go. So we've got this, here's the nucleus right here, and my proton is right here. And out here, at a distance of 5.29 times 10 to the negative 11 meters, the Bohr radius, is my little electron flying around here going this way, all right? And it's a negative charge. So the proton is attracted to the electron with a force, and the electron is attracted to the proton with force, but the centripetal action is keeping it going in its orbit like this, right? And we want to figure out what that velocity v is. We'll worry about that in a moment. Let's just take a look, and this is force 2. Notice they're attracting because they're opposite charges, right? Well, let's just calculate force 1. So when I calculate force 1, when I get done, which direction is it going? To the right, positive x. If I calculated F2, which direction would I say it's going? To the left, negative x direction. That's all. And we just put a negative sign in front of it. That's it. It's not that hard. Okay, so here we go. We'll say F1 is equal to K times Q1 times Q2 over R squared. Now these numbers get really, really dinky. Okay, they get really, really dinky. So we've got 9.0 times 10 to the 9th, that's K. That's what K is equal to, times 1.602 times 10 to the negative 19 times 1.602, and I just make them both positive, times 10 to the negative 19. I'm just taking the absolute values of both of them, divided by 5.29 times 10 to the negative 11 squared. Now I'm going to do it that way because this is the way I put it into my calculator. Watch and learn, people. So here we go. So I'm going to do this. I'm going to say, all right, we've got 9 second e to the 9th times 1.602 second e to the negative 19. Now I could close the parentheses and put a squared there, but I'm not going to do that. I can type it in again. It's 1.602 second e to the negative 19. Close my parentheses, divided by, here's the most important step. Double parentheses, 5.29 second e to the negative 11, close parentheses, squared, closed. That'll do it for me. All in one step there. And I get the force. Bang! 8.2, let's go with 8.25 times 10 to the negative 8. So F1 is equal to 8.25 times 10 to the negative 8 newtons. Well, that's not a very strong force. I mean, my goodness. It's like a nanonewton. Almost. Okay? I like saying that. It's a nanonewton. Well, it's 10 times a nanonewton. All right? Well, but we wanted to find the velocity. Aha! Of the electron. Well, we'll do this. Notice there's no masses in this, but we'll do this. We'll go, okay, well, that is equal to, do you remember this guy? mv squared over r for centripetal force. Hey, we're doing the centripetal force. Why? Because we rock. We're cool like that. All right? So we said this 8.25 times 10 to the negative 8. Now they probably did it all in all in one step times thing. Times r, which would be 5.29 times 10 to the negative 11 times r divided by the mass of an electron. Now remember, we're looking at the electron, so it's the mass of an electron, which is 9.11 times 10 to the negative 31 kilograms. Yes, I expect you to know these. Yes, I expect you to put them on your cheat sheet or your formula sheet yourself. By the time we're ready for an exam, you'll know the masses of a proton and the mass of an electron like the back of your hand, and this electric constant like the back of your hand. Okay? So there we got it all set up, because what we did was we said F1 is equal to, let's make it neater here real quick. Real quick. Don't panic yet. So we're going to do this. We're going to say, all right, and I'm timing myself up here to see how long it takes me to do one of these. All right. One of the problems I have that takes me a while is, one, I go into segues like this, and two is I'm looking for videos to show you and stuff that I think are kind of interesting. All right. So anyway, what do we say? F1 is equal to mv squared over r at that point. So we got F1 times r divided by m is equal to v squared. So I got to take the square root of the whole thing. F1r over m is equal to v. Make sure we take the square root over the entire thing. So I'm going to multiply this guy out. So I'm going to multiply out the 8.25 times 10 to the negative 8 times 5.29 times 10 to the negative 11. And this is newtons. This is meters divided by the kilograms. And I should wind up with meters squared, newton squared, divided by the kilograms. Or meters squared per second squared, divided by kilograms. And that should work. The 9.11 times 10 to the negative 31 kilograms. All right. Now remember, a newton is equal to kilograms meters per second squared. So inside this newton, I'm divided by the kilograms, so I get rid of that. So that's kind of in there. Multiplying by a meter, so I wind up with meters squared second squared, which is equal to v squared. So I wind up with meters squared second squared, which is what I want. Did a little unit analysis there. Then I'm going to take the square root of the whole thing when I'm done multiplying. So let's multiply this out. So I've already got this guy, so let's go times, because he's already there. 5.29 second e to the negative 11. I know some of my colleagues don't like it when you have numbers first and plug them in, but I think when you're learning, it's easier to see. There we go. Now, boy, that's going really, really fast. This is starting to scare me now, like I did something wrong, and I'm going to have to go back and read. Oh, I see what's wrong. I forgot the negative. The second entry. I forgot to put the negative sign in here. Negative 31. Did you see what scared me there? Because I wound up with 10 to the 50th. There we go. Times negative 10 to the negative 30. Now I'm going to take the square root of that. Oh, second square root, second answer. I'm kind of out of practice here. Boom, I get 1.67 times 10 to the negative 15 meters per second. Square root, took the square roots of both sides. I get 1.67 times 10 to the negative 15 meters per second. Pretty slow. In other words, it's just kind of not really moving. But it disappears, pops in on the other side, all kinds of weird stuff happens. Let's see how close we are to what they came up with. Whoa! This is correct. This is correct. What did I mess up? Oh, I see what I did. Okay, see what happens when I try and get too much stuff going at one time? All right, now take a look. I'm sorry. My bad. This is so wrong. Because I knew it was around 2.69. This is all correct. This is all correct. And when you plug it in to your calculator, that's all correct. I was like, what? Something happened when I did that, brought this in. So this is right. We got this. This is right. This is right. All my numbers right. It comes out to be 2.18. I thought it was really fast. Times 10 to the 6th, like 1,000,000 meters per second. 2 million meters per second. That's flying around there. So I'll show you where I fix that. All right, and that's where we're going to stop, except that this is force, and there are also vectors, 3 charges on the line, and we'll look at some of these problems when we come in. Now we're going to talk, and later we're going to talk about the electric field, and the best explanation I've ever seen of electric field is the Frankenweenie cartoon. That is your last thing to check out, your track 7 or 8, whatever it is. Okay? So out here, sorry for the screw up there. Of course, you know me, I had to screw it up at the end. All right? That was fun. Out here.